So let me start with a simple question. Why is Stephen Hawking so famous?
Hawking found a very interesting thing. The two main theories of our time are Einstein's theory of general relativity and the theory of quantum mechanics. What Stephen Hawking showed in 1975 was that these two theories are in contradiction with each other. So that is a very serious problem in physics. This problem is called the black hole information paradox, and it forms one of the key difficulties that we face in making a unified theory of everything.
And what is this black hole information paradox?
Einstein's theory of general relativity tells us that if you collect a sufficient amount of matter together in one place, it will collapse under its own gravity to make a black hole. So in a black hole, the matter suffers a runaway collapse. The denser it gets, the more the force of gravity pulling it in, so that it keeps shrinking and shrinking all the way down to a point. This is what we call a black hole. Now, what Hawking found was that in the region around this central singularity, you actually find that the vacuum is unstable, so it spontaneously creates pairs of particles. Because of this particle creation from the vacuum, the black hole slowly evaporates away by a process we call Hawking radiation. But because these particles came out of the vacuum, they actually carry no information about the matter which initially fell in to make the hole. So when the hole has completely disappeared by Hawking evaporation, we recover all the energy of the hole in the particles it has radiated, but we lose all the information. Now, this contradicts quantum mechanics because in quantum theory, the information of what you have is never lost. It may change from one form to another, but you can always recover the information by looking at what you have. And this seems to not be the case when black holes form and evaporate. Therefore, black holes violate quantum mechanics was the claim of Hawking, and this is called the black hole information paradox.
So now that we know a little bit about the black hole information paradox, let's talk about its resolutions. Let's talk about your resolution, the fuzzball resolution. What are these mysterious fuzzballs?
So if you want to actually attack this problem from first principles, you have to realize that two things go into this puzzle. The theory of gravity, because that's what made black holes, and of course the theory of quantum mechanics, because that's what led to the vacuum becoming unstable and producing this Hawking radiation. But once you put general relativity and quantum mechanics together, you have to deal with quantum gravity, so you have to start with a consistent theory of quantum gravity. The only theory we know of quantum gravity which is fully consistent is string theory, and then try to ask what happens if you make a black hole in string theory. And much to our surprise, what we found was you do not get Einstein's old picture of what a black hole should look like. Namely, all the matter in the black hole does not rush towards a central point under its own gravity. So with strings, the more energy you put into a string, the string actually can try to stretch. And as we compress the string, the energy that comes from this compression causes the string to actually become longer and longer. And instead of actually all being condensed down to a point, the string actually becomes a big fluffy ball, which is as big as the entire interior of the black hole. So in fact, the traditional picture of the black hole where all the mass is in the center and the vacuum around it is unstable actually doesn't emerge. What you get instead is a ball of string, which is more or less like a planet or a star. We could just call it a string star. With this actual picture of the black hole, which we got from string theory, there is no paradox, because now this object radiates from its surface just like a planet would radiate from its own surface, and then there is no information loss. So this automatically resolved the black hole information paradox. The word just comes from the fact that firstly it's a ball, and it's very fuzzy because it's very quantum. So that's just a name. But the important physics fact about the fuzzball is that this matter, the stringy matter, fills up the entire interior of the region which we call the horizon of the black hole. So instead of being a region of empty space with all the mass shrunk to a center, we actually have something which is a big fluffy ball.
The idea of a fuzzball breaks all our notions of a classical black hole. Why do we need such a striking solution? Why can't we solve the information paradox with the classical black hole, the black hole with a horizon and a singularity?
So in fact, this may have been one of the reasons why people did not manage to solve this paradox for such a long time, people were looking for solutions where they would keep the classical picture of the black hole with all the mass in the center and perhaps make small corrections to that coming from quantum gravity to try to somehow encode the information of the black hole in the radiation which was escaping. But in 2009, I proved a theorem called a small correction theorem, which showed that there is no such encoding of information possible. If you make any small change to the black hole, you can only encode a small fraction of the information. So in fact, if you actually want to solve the information paradox, you need a complete order unity correction to the structure of the black hole. And when we had actually worked with string theory, we found that was automatically happening. The fuzzball is a complete revision of what the structure of the black hole looks like. So this theorem, the small correction theorem, actually tells you need a complete change in the structure of the black hole. No small change to the structure of the black hole can ever help you. And then string theory automatically gives you this large change to the structure, and so the puzzle got resolved. So in that sense, unless you make a complete change to the structure of the black hole, you cannot get all the information. So initially people thought this was a very radical solution, that the strings are filling up the entire black hole and changing a classical picture of the black hole. But because of this small correction theorem, we realized it's not a radical solution. This is actually what you need.
So if the fuzzball paradigm completely solves the information paradox, then why hasn't it ended the dispute? Why are people still working on the information paradox?
Many people in the early days of the fuzzball paradigm thought that this solution was too radical. As we had just discussed, they were hoping to find a resolution to the puzzle where they would still have the classical picture of the black hole with only small corrections coming from quantum gravity. So when they were trying these other kinds of solutions, somehow nothing was actually working, but they were still hoping that some such solution along these lines would one day work out. Once we had the small corrections theorem, we realized that in fact no such solution is possible unless one changes one of the basic assumptions going into the theorem. So now the only possible alternatives to the fuzzball paradigm are of the following kind. You can have, for example, a wormhole that takes matter from inside the hole and dumps it far out near infinity and thereby recovers the information from the hole. But as long as you have no such non-local effects in the theory, the fuzzball paradigm is the only solution left for the information paradox. I think the fact that this theorem is not easy to absorb because it is based on subtle results in the theory of quantum information, I think that's what made it difficult for people to realize that they did require such a radical change to the picture of the black hole. But given this theorem, the fuzzball resolution looks natural, and I think more and more people are now coming to realize that.
So let's say fuzzballs are real. Then why do we observe black hole images as literal black holes in space? Why don't we see fuzzy balls which radiate as stars?
What we actually observe about black holes is not the black hole itself, because the interesting part of a black hole is the part inside the horizon. But since nothing can come out from inside the horizon in classical general relativity, there are none of the effects of what actually happen inside a black hole are ever supposed to be observed in classical general relativity. For example, when you take an image of the black hole, you see light which is coming from a place behind the black hole, going around the black hole and coming to our eyes. Its bending by the gravitational field of the black hole is what gives rise to the curious distorted images that we see. Or for example, if you look at gravitational waves, they come from a region which is about 3 times the radius of the black hole. So in fact, when we say we observe a black hole, that's not strictly accurate. We observe the physics of the gravitational field a bit outside the black hole. Now, if you have a fuzzball, that part never changes. The fuzzball only changes the interior of the horizon, but outside, the gravitational field is the same as the traditional black hole to a very, very high degree of accuracy. So observations of things like gravitational waves or the image of a black hole will not be able to show us the difference. The important difference has happened inside the horizon, and it's that difference which is important to resolve the information paradox.
Agreed. All the observations that one would get might not contradict the idea of a fuzzball. Then, how would it change the idea of falling inside a black hole? What would it look like to fall inside a fuzzball?
So this is a very complicated question. Okay. It's a slightly different question from Hawking's question. And that puzzle we have now solved because we don't have any region which is the vacuum which can become unstable. We just have a ball of strings which radiate from its surface. So the information paradox is over. But you can still ask a question, what happens if some heavy object falls into the black hole? At first, you might think the answer is very simple. If you have a ball of strings, you will fall onto the strings, get enmeshed in the strings, just like you would fall on the surface of a planet and get enmeshed in all the stuff which is on the surface of the planet. But here there's an interesting conjecture, which is called the conjecture of Fuzzball complementarity. And that conjecture is the following. In some indirect way, even though I have actually fallen onto the fuzzball and been absorbed into this ball of strings, I may continue to feel for a short time that I'm falling through empty space to a good approximation. But how can that be if I've actually changed and started becoming a ball of strings? Well, take the following as an analogy. Suppose in one room you have a piano, and in a different room you have a keyboard. Now, if you listen to the sounds coming from the first room, they will sound like a piano. From second room, they will sound almost the same, but actually what is inside that room is nothing like a piano. There are no strings and hammers hitting them. You in fact have just a bunch of electronic circuits. So two different things can mimic each other as long as they have the same frequencies. So if when I fall onto the ball of strings, the oscillation frequencies which I find for this ball of strings are approximately the same as the oscillation frequencies of the black hole in Einstein's theory, then one can mimic the other for certain purposes to a certain approximation. And so it's possible that one makes a model where you're falling onto a black hole, and to a certain approximation, you feel you're still going in, and the approximation becomes more and more accurate as the mass of the person falling in becomes larger as compared to the mass of a single particle. So in this sense, it's possible that the infalling observers who are themselves heavy continue to feel as if they're falling through a black hole, though in reality, they have been actually absorbed by a ball of strings. We do not know if this conjecture is correct, but it's very fascinating, and we would like to explore it further.
So now that the information paradox has been solved using the fuzzballs, what is the future of fuzzballs? And what is this Vecro hypothesis that you talk about?
The new thing we have learned from fuzzball physics is that the effects of quantum gravity don't just stay at the very small microscopic scales that people thought they stay at. They actually permeate the entire interior of the horizon, which could be several kilometers in size. But in a black hole, you don't just have two particles colliding, you have a very large number of particles all gathered together. And so what the lesson from the fuzzball paradigm is that when you put a large number n of particles together, the effects of quantum gravity don't remain at the Planck scale, they become some power of n times the Planck scale, and this can be a macroscopic scale. Well, now you can ask where else we might get such interesting effects. If you look up in the sky at our cosmology, you find that there is something called a cosmological horizon. And that's the horizon that tells us how far we can see in the universe today. But the cosmological horizon is very much like the black hole horizon. And so we might now ask if there are new effects coming up in cosmology at the scale of the cosmological horizon. So by taking the effect that we learned in fuzzball physics and now applying them to cosmology, we found some very interesting conjectures about how we might get some extra changes to physics at the scale of the cosmological horizon. And these led us to models where we might actually find resolutions to the cosmological constant problem. So understanding the structure of how fuzzballs play a role in the cosmological horizon, that story is called the Vecro hypothesis and is something I'm actively working on these days. And the interesting part of this puzzle is, why is it such a small dark energy that only today, when the universe has a fairly low density, it became something of importance? And interestingly, what we find when we apply fuzzball ideas to the universe is that you get a new source of energy where the universe transitions from the radiation phase to the dust phase. And that happened fairly recently. So that gives us we get extra energy when we transition from one phase to the other phase. And so the amount of extra dark energy we get through this Vecro hypothesis seems to be of roughly the right order as the cosmological constant we see in the sky today.
And what is the history of these fuzzballs? How was this idea conceived?
I was actually working on this problem for 7 long years from every possible angle. We took general relativity, we looked at quantum mechanics, looked at all possible theories of quantum gravity, trying to find some way that we could get the information to come out of the black hole. And each time we just ran up against a dead end. And then when we started actually using string theory to painstakingly build up each state of the black hole, we found a surprise. We found that whenever we tried to make a black hole using strings, instead of having all the mass rush to the center, we actually got this fluffy ball, which just wouldn't have any horizon, any singularity. It would be more like a string star. So this was a revelation to us and actually came out of very detailed calculations using string theory. But to get there, it also required many developments in string theory to happen. To study the black hole problem, you need to find what happens when you put a lot of strings together. So by the time the technology developed to a level in string theory that we could study questions like this, we had actually already found that none of the other approaches to quantum gravity were working. We finally took the bit between the teeth and started actually working with string theory, trying to actually make the black holes we get when we put many strings together. The fuzzball structure just popped out. So by now, many people have worked towards developing this fuzzball paradigm with many beautiful results which have explored the structure of fuzzballs in many different ways.
Thank you very much for this session. Could you please motivate our young audience over there to join our efforts in solving these interesting problems in physics?
I think this is a very interesting area to work in because this is really the cutting edge of physics where we are actually trying to find out how gravity and quantum theory and everything works together to make the final unified theory of everything. I think the most important aspect of this kind of work is that you have to be extremely sincere. You may have an idea one day, you may work with it for a week, a month, sometimes a year, but you yourself have to keep questioning, could there be a mistake in it? And very often you will find that it's wrong. And then you have to go back to the drawing board and start again. So as I was saying, I worked for 7 years before we got any glimmer of how this whole thing might be resolved. And in those 7 years, each morning I would wake up with a bright idea thinking it has to work this way. And by evening or by the end of the next week or the next month, I would find it doesn't work. So somehow one has to be extremely patient and extremely critical of one's own possible errors so that one can just keep going down and down and down till you actually find what is the real resolution of a puzzle. Because there are many apparent resolutions that come to you. This might work or that might work, but you have to be very critical of your own ideas here because nobody else can find your mistakes. You're the only person who can find your mistakes. But at the end of it, it's very rewarding when you actually find how something works. It will actually change the direction of physics forever. So I really encourage all young people to take a thought at going into these directions.